Hi everybody, Mrs. Pesic here. We are looking at section 5.7, radical functions. All right, in section 5.7, our objectives are to graph radical functions and inequalities and to transform radical functions by changing parameters. The vocabulary for this section include radical function and square root function. So first of all, let's do a little recall. You know that exponential and logarithmic functions are inverse functions. All right, and you know that quadratic and cubic functions are going to have inverses as well. So the graphs below show the inverses of quadratic functions, quadratic parent functions, and cubic parent functions. So, for example, here, this is the original function y equals x squared, or f of x equaling x squared, looks like that. And its inverse, which is when you switch all of the ordered pairs, switch all the x's and y's, you will end up with a graph that looks like this. So this function is the inverse of f of x equaling x squared. Up here, you know the basic graph for x cubed function looks like this. This is the graph of y equals x cubed. And then its inverse would be a reflection over the line y equals x. That's where all the x and y coordinates have been switched, and that graph would look something like this. All right, so that's the inverse. Here's the problem though. In this example right here, with this one, notice that this one would fail the vertical line test. If I draw a vertical line through that graph, it's going to hit that graph in more than one point. So that inverse is not a function. It is the inverse of x squared, but it's not a function. All right, so we're going to see how we can get around and get away with that. All right, it says, notice that the inverse of f of x equaling x squared is not a function because it fails the vertical line test, as I just demonstrated. However, if we limit the domain of f of x equaling x squared to just x greater than or equal to 0, then its inverse is going to be a function. So when we limit the domain, let's go back and look at the x squared function. Instead of taking the whole thing like this, if we just take from x equaling 0 and above, that means we really only have this right half of the parabola, then its inverse is going to be just this top half of that parabola. And so this is going to be a function. So this original function is f of x equaling x squared, but remember only for x greater than or equal to 0. And this function is f of x equaling square root of x. Or you could say it's the inverse of the original function, so you could write f inverse of x. All right, a radical function is a function whose rule is a radical expression. A square root function is a radical function involving the square root of x. The square root parent function is f of x equaling square root of x. The cube root parent function is f of x equaling cube root of x. Let's take a look at this example. We're graphing a radical function. The directions say graph each function and identify its domain and range. So for this problem, if we are graphing f of x equaling the square root of x minus 3, and I'm hoping you are going to be putting this on graph paper. All right, if we're graphing f of x equaling square root of x minus 3, we're going to make a table of values. We're going to plot enough ordered pairs to see the shape of the curve. And the hint here is that because the square root of a negative number is imaginary, choose only non-negative values for x minus 3. That tells me, if I'm going to plot a few points here, I'm making a column for x versus f of x, that the smallest x value I could choose would be 3. Because 3 minus 3 is 0, so I'm really getting square root of 0, which is 0. What if I choose 4? Then I get square root of 4 minus 3 is square root of 1, which is 1. And what if I choose, let's see, how about 7? I'm choosing these carefully because I like getting perfect squares as my answer. So if I do square root of 7 minus 3, I get square root of 4, which is equal to 2. And how about we do one more? How about 12? If I choose 12, I get square root of 12 minus 3. That's square root of 9, didn't I choose well? I ended up with a nice integer of 3. So with the graph then, the graph is going to be 3, 0, 4, 1, 7, 2, and 12 is a little bit off my graph, but 12 goes up to 3. So the graph is going to look like this. It really is half of a parabola opening to the right, just the top half there. All right, what's the domain for this function? Well, as you saw, the smallest x that we could plug in was 3, so our domain is going to be from 3 all the way up to positive infinity. Notice I have the bracket here for 3, which means the 3 is included in the domain. All right, and then the range is going to be how low does the graph go, how high does the graph go. It goes from 0 all the way up to positive infinity. So we're going to say negative infinity. I'm sorry, no we're not. We're going to say 0 to positive infinity. All right, because the lowest it goes is 0, doesn't go any lower than that, and it goes up to positive infinity. All right, let's take a look at this example. F of x equaling 2 times the cubed root of x minus 2. So for this example, we're going to, again, plot some points here. If I choose x to be, let's say, let's see, what would be good x values to choose? Let's try 1. Let's try -6. Let's try 3. Let's try 10. I'm choosing those. How did I choose those values? By the way, remember, you could type this into your calculator, pull up a table, and get your own ordered pairs. I'm just choosing these because I'm hoping that they'll turn out to be nice integers. Let's see how I did. So I get 2 times cubed root of 1 minus 2. That's 2 times the cubed root of -1. Well, cubed root of -1 is -1, so I get 2 times a -1, which is equal to -2. All right, so remember, cubed root of -1 is -1 because -1 times -1 times -1 is equal to -1. All right, what about if I plug in -6? If I plug in -6, I get 2 times the cubed root of -6 minus 2 is a -8. The cubed root of -8 is actually -2, so I end up getting -4 for my answer there. And then what about plugging in 3? I get 2 times the cubed root of 3 minus 2. That's 2 times the cubed root of 1. That's 2 times 1 is 2. And if I try 10, I get 2 times cubed root of 10 minus 2 is 8. And that's 2 times cubed root of 8 is 2. So I get +4. So if I plug in these values, or graph these values, I should say, I have the ordered pairs 1, -2, -6, 1, 2, 3, 4, 5, 6, -6 goes to -4, 3 goes to 2, and 10 goes to 4. And my graph is looking something like this. All right, by the way, one more value that I could have plotted, but I didn't, was just actually plug in 2, because then I get 2 times the cubed root of 2 minus 2 is 0. I get 2 times 0, which is 0. So I will have my x-intercept right here at 2, 0. So what's really happened to this graph? What's happened to this graph, if you look at the transformation, we see x minus 2 here, which means we are shifting what direction? 2 to the right. And I see this 2 out here, and this 2 means we have a vertical stretch by a factor of 2. So my original cube root function has been vertically stretched and shifted to the right 2. So that's our graph. Domain here is all real numbers, -infinity to positive infinity, because I can choose as far left as I want, as far right as I want. And the range is also -infinity to positive infinity, because this graph is going to go down as far as I want to go, up as far as I want to go. All right, here's your first notes must do. Graph this function and identify the domain and range. So I want to see this on graph paper. Square root of x plus 1, make a table of values and sketch a graph on graph paper. When you're done with this example, go on to the next page. The graphs of radical functions can be transformed by using methods similar to those used to transform linear, quadratic, polynomial, and exponential functions. This lesson will focus on transformations of square root functions. All right, you should be really getting the hang of this, I hope, because you've seen this multiple times this year. You know that if you have a function and you add a constant to the end of the function, that's going to shift it up or down depending on whether that constant was positive or negative. If you have a function and you subtract some number or add some number to the x itself, not just at the end of the function, but to every x in the function, that shifts it to the left or the right. If you take your function and you multiply it by some constant, like this, a times f of x, you know that that gives you a vertical stretch or a vertical compression. So they give you some examples of this, like 6 times square root of x is going to be a vertical stretch by 6. 1/2 times the square root of x is going to be a vertical compression by 1/2. For the horizontal stretch or compression, they say if you take every x in your function and you multiply by 1 over b, that's going to be a horizontal stretch if the b is greater than 0 or greater than 1. So, for example, square root of 1/5 x is going to be a horizontal stretch by a factor of 5. And if you have square root of 3x, that's a horizontal compression by 1/3. All right, and then reflections. If you take the opposite of a function, that reflects it across the x-axis. If you take the square root of negative x, like right here, that's going to be a reflection across the y-axis. This is kind of interesting to look at on your calculator, these last ones that is, because remember our parent function for this set of problems is f of x equaling square root of x, and we graphed that at the beginning of this lesson, and that graph looked like this. All right, but if you have, and you can check this with your TI Nspire, if I have a different function like g of x equaling negative square root of x, that's this situation, it's going to be a reflection across the x-axis. So that means that function, g of x, is going to be down here, looking like this, reflected over the x-axis. But if we have, let's say, h of x, and if h of x equals square root of negative x, then that's going to be reflected across the y-axis, so that graph is going to look something like this. All right. Okay, so transformations of square root functions are summarized below. Maybe you'll find this helpful because they put it all together for you. So if you have x minus h, that is going to be a horizontal translation. If you have a plus k, that's going to be a vertical translation. If you have a number out in front of the function like this, that's going to be a vertical stretch or vertical compression. And if the a is less than 0, that's going to reflect across the x-axis. And lastly, if you have something being multiplied by the x inside the radical, that is going to be a horizontal stretch or a horizontal compression. And if the b value is less than 0, it's going to be a reflection across the y-axis. All right, so let's take a look at this example. Use the graph of f of x, using the graph of f of x equaling square root of x as a guide, describe the transformation, and graph the function. So for this first one, we see the general parent function is right here, but what's being done to it? It's got this plus 5 added on at the end, so that means that it's going to be, oh boy, that means it's going to be shifted up 5 units. So my parent function, that's what I wanted to see. Let me erase what I wrote. So my parent function is here in blue, but since we've shifted it up 5 units, g of x is going to look like that. All right, what about the square root of x plus 1? There's the parent function in blue, and the square root of x plus 1 is going to be shifted up 1 unit. All right, that brings on notes must do number 2. Using the graph of f of x equaling square root of x as a guide, describe the transformation and graph the function. Again, I want to see this graphed on graph paper. So g of x equaling 1/2 square root of x. Remember, you're going to start your graph. I'm just giving you some hints here. I want to see the basic parent function, which I'll call f of x equals square root of x. Goes through 0, 0, 1, 1, 2, 3, 4, 2, 5, 6, 7, 8, 9, 3, and so on. Remember, it's that half of a parabola like this. All right, and then you are going to graph now this function, g of x equaling 1/2 square root of x. So on your graph paper, I want to see what that looks like compared to this function. So you can put them both on the same graph. All right, moving on. Now we're going to apply multiple transformations. So for this one, it says using the graph of f of x equaling square root of x as a guide, describe the transformation and graph the function. Well, here I see x minus 4 inside the radical. That means a shift to the right 4 units. And I see this negative out in front, which means the graph has been reflected over the x-axis. So here's our original parent function in blue. Remember, it goes through, as I mentioned just previously, goes through 0, 0, 1, 1, 4, 2, 9, 3, right? And then the new graph is going to be shifted 4 units to the right, which is going to be like this, and so on, right? So that's shifting 4 units to the right, but then we want this whole thing reflected over the x-axis, so it does end up looking like this. All right, let's take a look at this example. We have square root of negative x plus 3. Since we have negative x underneath the radical, that means that we have a reflection this time over the y-axis. All right, so again, instead of that square root function, looking like this, it's now going to be looking like this, reflected over the y-axis. But we're also adding 3 on, so that's going to shift that whole graph up 3 units. Let's see what that looks like. There it is. So we are reflecting this graph. Here's the original function right here. We're reflecting this over the y-axis, which puts it looking like this. And then we're shifting that graph up 3 units, so it's looking like this. All right, example 4, writing transformed square root functions. Use the description to write the square root function g. The parent function f of x equaling square root of x is reflected across the x-axis, compressed vertically by a factor of 1/5, and translated down 5 units. So this is your chance to write the function. You're going to write the function g, so it's g of x. The parent function is square root of x, but we want this function reflected across the x-axis. Well, that means that we want opposite of the square root of x, but we also want it compressed vertically by a factor of 1/5, which means we really want 1/5 in front of the radical, not inside the radical, and we want it translated down 5 units, so that means we want -5 on the outside. So the answer for this one should be g of x equaling -1/5 square root of x minus 5. All right, that brings up our last notes must do. you're going to use the description to write the square root function g. The parent function f of x equaling square root of x is reflected across the x-axis, and it is stretched vertically by a factor of 2 and translated 1 unit up. So you do not need to graph this, but you do need to write out what g of x function would look like, just like we did in this previous example. All right, that completes the notes for section 5.7. Thanks for watching. I hope you watched all 3 videos, 5, 6, 5, 7, 5, 8, and took good notes on all of those, and we'll see you next time.